Algebra 2 students, we are starting Unit 8 on polynomials. So the notes packet, this first little part actually gives you a kind of a good clue as to what we're working into. So different degrees of polynomials and what those graphs look like. So the first couple of days sort of mush together. So we're just going to go until we get to where we need to, and then we'll stop and call that a quits on day 1. All right. But the goal for day 1 is intro and talking about power functions. And then we will go from there. So moving on over to page 1 in your packet, the first thing you want to make sure is that we even recall polynomial functions we've covered already. So when they say that they're in this format, what it really means is that, you know, the number in front and the exponent can change. So a degree 1 is essentially a linear function, and that typically is what we write as mx plus b. In this form, it would just be ax plus b, but same difference, right? Degree is talking about the highest exponent. So in a linear function, the highest exponent is 1, which is why it's a degree of 1. So degree of 2, the highest exponent would then be a 2. So like ax squared plus bx plus c, and that's a quadratic function, which we just spent a ton of time talking about. We're going to talk about what happens when the exponents go higher than that. So the next thing that you're looking at here is called a power function. So a power function right here has the form of y equals a times x to the b power, where a can't be 0 because it'll wipe it out, and b has to be greater than 0. So just an example of like what you could end up seeing is, you know, 2 times x to the 4th, that would be a power function. Or a lot of times it might be messier than that, you know, negative 5.12 and then x to the 7.4 or something crazy like that, all right? It says, note, the a value is simply a coefficient of the function, and then the overall shape and behavior depend on the exponent, really. That's the key there, all right? So this is just going to be some sort of like stretch factor, essentially. What the shape looks like depends on the power. So that's what we're going to look at down here. It says fill in the tables for each of the following given, but the tables are actually done for you. That was just for time's sake. So when you have like the first function, f of x equaling plain old x, right? You can see all the x's and y's match. So if we were to sketch that, think about what the line y equals x looks like. It's that perfect diagonal where 0, 0, 1, 1, 2, 2, and so on. So you just end up with this guy. And you could use your calculator. Whoops, a little off the screen there. You could use your calculator to help you out with that if needed. The next one, the parabola, you have g of x equals x squared. Again, we know how to graph this without even probably using the table, but it's here if you need it. So like 1, 1 and 2, 4 and so on. And then if you keep going, some functions we haven't looked at yet. So when we have h of x equals x cubed, they're just plugging in and cubing each value. So negative 27, negative 8, negative 1, those values should look really familiar from when we did sum and difference of cubes. Now, if you think of plotting this, 0, 0, like 1, 1, negative 1, 1, but then the numbers get really big really fast. It shoots up to 8 and so on. And this one gets really small really fast. So it kind of looks like this here. And you could absolutely use your calculator to kind of help you sketch that graph if needed. As for the next one, y equaling x to the 4th, or in this case, r of x equaling x to the 4th. If you look at the values, when you raise something to the 4th power, everything's coming out positive. So you have 0, 0, you have, you know, the 1, 1, and then if we go over to 2, it comes all the way up to 16. And then at negative 2, same thing. So it actually looks really similar in this format to the parabola itself, right? That can change depending on when you change other numbers, but for the basics. All right, and then this last one, if we plot s of x equaling x to the 5th. So here you can look at the values. They have a ton in common. You're seeing this 0, 0, 1, 1, negative 1, negative 1, but then it goes negative 2 way down to negative 32. And then this one, positive 2 way up. So it's going to look really similar to the x cubed function. Oops. But it's stretched out even more. right? So some things that we should start to notice is there's kind of a pattern here that you kind of get this extension and then parabola, and then an extend and then parabola, and then an extend. So you can probably guess what that x to the 6th right now would actually look like, right? So flip it on over to the next page. Let's talk about some of these little details here. So it says, note which of the functions in the last example were even, which ones were odd. All right, well, even functions, we're going back a little ways. Even functions means they have y-axis symmetry. So when I bring back that page, the ones that had nice y-axis symmetry was the x squared, the x to the 4th, the ones with even exponents. All right, so it had y-axis symmetry. That's what an even function is. It also means that the point xy and the point negative xy are on the graphs, but those were all the ones that had even exponents. So y equals x squared, y equals x to the 4th, not probably super shocking there. As for odd functions, that was what was called origin symmetry. It's easy for me to show this because my paper is separated. So if I take and I flip this thing upside down, it looks exactly the same for the odd functions upside down as it did right side up, whereas the even functions are literally upside down. All right. So origin symmetry meant that the point x, y, and the point negative xy are both on the graph. And the ones that were odd were the plain old y equals x, y equals x cubed, and y equals x to the 5th. So the exponent kind of determines the possibility of if it'll end up even or if it'll end up odd, right? But that's only for when it's basic. If you add on any other stuff to these, it can kind of change things, right? But that's at least a good jumping off point to go from. This next little part, then, you've got a little multiple choice. Just says, which of the following power functions is shown in the graph below? Explain your choice. Do this without the use of your calculator. So what I'm expecting you to notice when you're looking at this, right, is it's got kind of a parabolic shape. So right there, we're talking about an even function. So when you look at your choices, any odd exponents, we can get rid of. The fact that it opens down, that should be the next thing that clues you in. So if it's opening down, we want to see that negative exponent. And so choice 2, that would be our answer there. So what that helps us talk about in this next little piece, the idea when we say like it opens down, and when it says the blank of the polynomial describes what happens to the graph as the x values get really big and really small. We talked about this a few units ago. That's called the end behavior. So it's not wrong to say it opens down, but it's actually discussing the end behavior without even maybe realizing it. So like as x gets really big, so as I look to the right for this particular graph, the y value was getting really small, right? And then as x goes to the left, or as x goes to negative infinity, the y value is still getting small. That's an example of the end behavior for this example. So I'm going to say, for example 2, we would say as x headed to infinity, y went to negative infinity. And then as x went to negative infinity, as we were going that way, the y value still was heading to negative infinity. Right? So a little review from a few units ago there. Sometimes those are lovingly called the tails of the graph as well. So what are the tails doing? They're both heading to negative infinity. Right? As we keep moving in that same thought pattern here, it says the polynomial functions that have that format. Let's look closely at the 3rd degree ones and the 4th degree ones. So the 3rd degrees are called cubic functions, and the 4th degree ones, those are called quartic. Or I guess cubics, plural, and quartics, plural. All right, so as we look at these down here, you can see in the chart that they're giving you like the ax cubed plus bx squared plus cx plus d. So you just keep working your way down the alphabet. And what we want to look at is what we saw on the first page. So I'm going to grab my calculator and I'm going to clear out what I have in here and I'm going to put in an x cubed. So if I put in x cubed, I'm just going to zoom 6 this so you guys can kind of see what this thing looks like. So there's that little shape that we drew on the first page, all right? So when we think about it, when it says when a is greater than 0, so that means for a positive x cubed, we sort of get this little shape right here. So when you, oh, sorry, my phone's next to me. Siri thinks that I'm talking to her. I'm not talking to you. All right. So when x is heading to infinity, so as we go to the right, look at where y is going. It's going on up to infinity. As x is heading to negative infinity, so as you go to the left, where's y going? Well, y is heading down to negative infinity. So that's what's happening with the tails of the function. If a is negative, though, so if we type in and we make this a negative x cubed, then look at what happens. Now the graph is the opposite kind of where we just were. So negative x cubed means now, instead of heading up to the right, it's heading down to the right. And so in this case, what we can say is as x heads to infinity, y is heading to negative infinity, and then vice versa. As x goes to negative infinity, y is heading on up towards positive infinity. But either way, what we should kind of notice about the tails is that when one side's heading up, the other side's heading down, and then vice versa. So I like to say that when you have an x cubed, or more specifically, when you have any, or I should say more generally, any odd function, the tails always go the opposite. So one's going up, one's going down. So how does that compare to when you have an x to the 4th? So let me grab my calculator and change up what I got going on in here. So x to the 4th, if I go and hit my graph, so when we have a positive x to the 4th, we said it sort of looks like a parabola that got like a little flattened at the bottom. Looks a little smushed there, right? But what I care about is as x goes to infinity, y goes to infinity. When x goes to negative infinity, y is still going to positive infinity there. Now think about when the a value is less than 0. So if this was a negative x to the 4th, you should already be picturing in your head what you're expecting to see. Just like a negative x squared, now that parabola-looking shape opens down. And so whether I go to positive infinity or negative infinity for x, these both go to negative infinity. So what I want you to take away from this is just like an x squared function, in this case an x to the 4th function, when you have even exponents, those tails are always going in the same direction. So both up or both down. All right. So this way, if I said like, what would an x to the 6th function look like, or an x to the 12th function, or whatever, you could think to yourself, right, even function versus odd. Okay, at least I know how the tails are going to go. They're going to go same direction or opposite direction, all right? This is actually a great spot to stop for the end of day 1. That's enough to get us through and be able to manage day 1 homework. And then we will pick back up and keep going in the next video. Thanks so much for watching.